Okay, new chapter, new lesson here, equivalent trigonometric expressions. And what we mean by equivalent trigonometric expressions is two trigonometric expressions that are equal to each other. They're equivalent to each other. And you'll notice I've started the lesson off a little different than what your worksheet, if you print it out, has. It starts off with setting the stage and does some examples here. And I'm going to get to those, but I just want to really frame what I'm up to right off the hop and really explain what this title means by equivalent trigonometric expressions. So I want you to grab a calculator. If you don't have a calculator, get your calculator going right now. And we need to get it into degree mode. And for the purpose of this example, what I want you to do is, in your calculator, I want you to type in sine of, say, 40 degrees. And I'm going to punch that in my calculator. When I get sine of 40 degrees, well, I get this crazy decimal, and I really want to get all those decimal places down because I'm up to something here. 64278,76097. Okay. And now I'm going to do sine of another angle, and it's going to seem like maybe I've chosen it at random, which I haven't. I just know what's about to happen here. I'm going to go sine of 140 degrees. And when I type in sine of 140 degrees into my calculator, I get the same exact thing. Maybe you saw that coming because of the name of the lesson, but also because of the angles I chose. Now, how is this happening? Well, when I draw a little sketch of sine here, sine does something like this. It goes up and then down and then down and then up. And then it keeps doing that again and again. And I want to draw your attention to what's happened here is I chose an angle of 40 degrees and I found its value was about 0.62. And it's not much far later where the graph's going to go up and then come back down and come to that value again. So when we say equivalent trigonometric ratios, all trig graphs are going to have this feature to them that they repeat, and every possible answer can happen many, many times. Better than that, I'm going to try another angle here. I'm going to go for sine of 220. And sine of 220, when I punch that in, is negative 0.642787697, which is right about here, where I get the same answer again, but only the negative version of it. And that can happen one more time in the first cycle. Somewhere about there, and I know what to do, and maybe you're getting an idea of what to do to get this next answer, is I think that next answer is going to be at sine of 320 degrees. And if you type in sine of 320, there it is, negative 0.642787697. See, exactly the same answers. It's just that they've changed from positive to negative answers. We're going to talk a lot about this, about why this is happening. Well, I hope I already explained why it's happening. It's just how we can use it. But just to go one step further with this, it's not just about sine. You might have already figured out what I'm up to with sine, and that's okay if you haven't. I'm going to explain it all. I'm going to go cosine of 50 degrees, and I'm going to explain this during the lesson as well. But cosine of 50, watch what I get. There it is, 0.642787, 642,787,6097. Why is that happening? Well, cosine goes through the same value sine does. It does them in a different order, but whatever that value is, it's going to come out some point in cosine, and the negative versions are going to be there, and it's going to come back to it at some positive number later on. So there's lots of equivalent, and that's what we're talking about in this lesson, equivalent trig ratios, and we're going to learn how to find them. That's what we're going to be up to. Now, just to give away what I was up to here, what was I using here? When I went to this sign here, I just went to its 180 minus 40, and here I went to 180 plus 40. I always was using that 40-degree angle to get these other angles. So it always came back to that original 40 degrees, and that 40 degrees has a name. It was called the related acute angle. And I'm going to draw them and relay it out for you and everything like that. So, but I just want to bring that back up. That's what we're really dealing with here. Now, what happened here? Here, to go to cosine, I had to go 90 minus 40, not 180 or 360. And again, if that's all very confusing how I'm coming up with that, well, that's what the lesson's going to do. It's going to really explain all those things. Okay, so really to frame what I'm up to here, express each of the following term in terms of the related acute angle, and you don't need to evaluate. A sketch will help. I will evaluate them at the end, just to really show off what's happening. But a sketch really, really helps here. Now, when you first do these, I actually find 2 sketches are helpful. So as I go along, we may reduce it to only having 1 sketch with 2 things on it. But you'll see as it goes along. Okay, so they said find tan of 220. So if I draw 220 degrees, it's going to be 180 and 40 more. There's, oops, I didn't want to write 220, 180 in there. I want to write 220 in there. There's the 220. It went 180 degrees, but then it went 40 degrees more. And this 40 degrees more that it went past the x-axis is called the related acute angle. So for tan 220, the related acute angle is 40 degrees. That is, if I draw the angle 40 degrees, and I draw the angle 220 degrees, they will both result, and this is the most important sentence of the whole lesson, I think, they will both result in a triangle that has a 40-degree angle with it. What that means is, whatever the tan of 220 is, it will be the same as whatever the tan of 40 is. So this and this same answer, because they both give the same triangle. And that's why the related acute angle is so important. A 220 angle will give a 40-degree angle in the triangle, and a 40-degree angle will give a 40-degree answer in the triangle. So tan of 220 equals tan of 40. Well, okay, hang on. It might have changed from positive to negative. See, that's what happened up here sometimes, is we went from positive to negative. How will we know if it switches to positive negative? Well, every time you draw one of these axes, draw the cast rule on there and decide whether your answer is going to be positive or negative. So when I put the cast rule on there, I see that 220 ends up in a tan positive quadrant. So tan of 220 will be positive. Tan of 40 is in a all positive quadrant, so it's going to be positive. So tan of 220 and tan 40 both have the same positive answer, so these will come out to be equal. Well, don't believe me? Well, I'm going to evaluate them. If I go over and I type tan 220 on my calculator, I get some ridiculous negative. Oh, I typed something in wrong. Something extra came on my screen there. Tan 220. I was like, well, how can it be negative? And I was staring at my screen and I realized I typed something wrong. Okay, tan of 220 equals 0. Oops. 0.839,099,6312. And if I type in tan of 40, I get the exact same thing. And that's not what we were trying to find there. So we're not trying to find that. This says you do not need to evaluate. I did here, but only to prove the point that tan of 220 and tan of 40 come out to the same answer. How do we know how to find these angles? We use the related acute angle. Find out the related acute angle for the first one. And again, hugely important sentence here. Find the related acute angle for yours, and that will lead you towards the answer. Let's try another one. Cosine of 150. Through all the steps again. So if I draw 150 degrees, be right about there, there's 150 degrees, and it results in a triangle that has a 30-degree angle in it. So the related acute angle is 30 degrees. And you can see, I could probably do this all in one diagram. I could answer this question in one diagram. But I'm going to draw the second diagram so you can really see what's happening. You see? When I draw 150, it results in a triangle that has an angle of 30 degrees in it. And of course, if I draw 30, it'll result in an angle, a triangle that has a 30-degree angle in it. That means whatever I get from cosine 150, I'll get the same thing for cosine of 30. Well, okay, again, just to reiterate, it might have changed from positive to negative. It'll give the same answer, but it might, instead of being positive, it might be negative now. And how do you check? Well, you just draw the cast rule on every time, and you say, okay, in this quadrant, 150 will give a negative answer for cosine, whereas 30 will give a positive answer for cosine because it's in the all positive quadrant. So if cosine 150 needs to be negative, we need to put a negative in front of the cos 30 to be able to get the answer we're looking for. the cosine of negative 150 has to be negative of the cos of 30 because the cos of 30 is going to come out to be positive. If you type this in your calculator, cos 150, you'll get the negative answer, negative 0.866. And if you type cos 30 in your calculator, you get the positive one. So the cosine 150 is the negative of the original answer. Okay, keep going. Same steps every time. Sine negative 200. The procedure is draw the angle given, negative 200, right about there. And by drawing it, you should be able to come up with the related acute angle, and more importantly, the triangle that you would get the answer from. And in my second diagram, which again, if you start to do these and you feel like you only need one diagram, that's fine. Both of these will give the same answer. Negative 200 gives a triangle with a 20-degree angle in it. 20, of course, gives a triangle with a 20 in it. That means whatever sine of negative 200 is, it will give the same answer as sine of 20. They will both give the same answer because they come from the same triangle. Well, okay, they might not, it might have changed from positive to negative, so we just have to check that. And we look at the quadrants and we say, okay, sine of negative 200 is in a sine positive quadrant, so it'll be a positive answer. Sine of 20 is in an all positive quadrant, so it'll give a positive answer. So truly, sine of negative 200 is equal to sine of 20. It hasn't changed from positive to negative. Okay, I did all of those in degrees so that radians wouldn't get in the way of your understanding. Now, if you get all that, all I'm going to do now in the next couple is just switch to radians and do some radian thinking here, which I'm going to review the radian thinking in here as I go. So the steps are the same. First, draw the angle they're talking about. And if you're having trouble drawing these, here's the way I'd like you to think about them. We know that this angle here is pi. And in this case, I'm going to think of pi as 3 pi over 3. Pi can be thought of as a lot of things. It can be thought of as 2 pi over 2, or 3 pi over 3, or 4 pi over 4, 6 pi over 6, whatever's convenient for the question you're doing. In this question, they want 2/3 pi, so it's good to think of pi as 3/3. So then where will 2/3 be? Well, if I want 2/3, it's right about there. 2 pi over 3. What's the related acute angle in the triangle? Well, 3 pi over 3 all the way to the axis there. I only used 2 pi over 3, so what's left? 1/3 of that pi, or pi over 3. So, the angle 2 pi over 3 results in a triangle with related acute angle pi over 3. If I draw pi over 3 in the first quadrant there, it's also a triangle that has angle pi over 3. And what that means is sine of 2 pi over 3 will give the same answer as sine of pi over 3. Well, as long as it hasn't changed from positive to negative, and a quick drawing of the cast rule tells me, oh, both of these answers will be positive, so these are the same number. They don't need to be changed. One doesn't need to be changed from positive to negative. Well, that's the example I give. Any radian example, if you follow along like that, can be done just the exact same way. The steps are the same. You just have to think in radians. So the only other example I want to talk about in this part of the lesson is something where it's not just sine, cos, or tan, where it's secant. And there's a couple of strategies you can use here, but let me show you a couple of those strategies. Okay, so first step is the same. Draw the angle they're talking about. And now in this case, there's the angle pi, which in this example I'm going to think of as 4/4. There's 4/4 of pi, 4 out of 4. But we want 5 over 4, which means I got to go a little farther than 4 over 4. There's my angle 5 pi over 4. What's the related acute angle? Well, to the axis, it would have been 4 pi over 4. I went to 5 pi over 4, so I went an extra pi over 4. So the related acute angle is pi over 4. My second drawing gives the triangle just pi over 4. And what I want to say is, whatever that 5 pi over 4 results in a triangle that has pi over 4 as its angle. Pi over 4, of course, is a triangle, is an angle that has a triangle with pi over 4 in it. What that means is secant of pi over 4 gives the same answer as secant of pi over 4. Now, did it change from positive to negative? There's the big question. And you got to sort of work with the cast rule a little bit and say, okay, well, here's the cast rule. And cast says in this quadrant only tan is positive. And with that, Cotan would be positive. So the CAST rule doesn't mention those reciprocal trig ratios. You just got to sort of think those through. Tan and cotan would be positive. What that means is secant would be negative. So the answer for secant of 5 pi over 4 must come out to be negative. So we need a negative in front of that to be able to get our true answer. Some people look at that and say, oh, you're saying secant pi over 4 is negative. No, I'm not. I know this part is positive. I know that part's positive. So if I'm going to get a negative answer over here, I got to put a negative in front of that secant pi over 4 because it is positive. Okay, so dealing with secant and cosecant cotan, no real difference there. You just have to stare at the CAST rule and remind yourself what's going on here. So like, for instance, in this cosine quadrant, you just have to remind yourself that also means that secant would be positive as well. But the CAST rule can lead you there. Okay, making the generalization to x, though, it's really where we want to go with this, is we don't want to talk about specific angles all the time. We want to talk in general what happens with an angle. And if that seems confusing, well, yeah, it is confusing because when I put a general x in there, it gets a little weird to talk about it. So for now, we'll stick to acute angles of x. We'll just say, okay, let's just do it when x is acute for a while, and we'll draw the pictures and see what kind of results we get. And I need to tell you, it doesn't matter for all the results we're going to get. I'm going to say that at the end, whether x is acute or not. It's just the diagrams get really, really tough to draw. I can draw them with acute x pretty easy. Here's what I mean by that. It says, draw the angle pi minus x. What that means is, there's pi. I want to draw an angle that's pi, subtract an acute angle. So that's in this quadrant here. Someone's immediate response goes, well, how do you know it ends up in that quadrant? And that's because we decided it was going to be acute. For all the diagrams I'm doing, we're going to be an acute angle, meaning smaller than pi over 2. Smaller than 90 if you're having trouble with radians. I need a smaller angle than 90, which means when I go pi minus x, there's the angle pi minus x. It doesn't get all the way to pi. It's got to be pi subtract a little bit. The next one they want is pi plus x, so then I've got to go here. I've got to go pi, but then I got to go an extra little bit x. The next one they want is 2 pi minus x, so I got to go all the way around to 2 pi. 2 pi would be a full revolution. They don't want that. They want me to come back a little bit from that, so it's somewhere in there. 2 pi would be all the way around. I don't quite make it. They want x taken back out of there. The next one's 2 pi plus x, which would be all the way around and x more. So there's 2 pi plus another x. There's the angle 2 pi plus another x. And again, there's the x in there. And then finally, negative x. Ooh, that's moved off my screen a little bit. There's negative x right in there. Now, what do the 5 angles all have in common? Well, the only thing they have in common is they end up with the same related acute angle when it's over. Oh, and I made a mistake drawing one. I hope you noticed that along the way. I said x there, but I drew a pi, so it's all x's. Do you know notice how the related acute angle in all these, the angle between that terminal arm and the x-axis is always x. They all have related acute angle x. Therefore, sine, cos, and tan of all of these angles we'll be able to switch over just to x. Like, for instance, cos of pi plus x is the same as cos of x. Those two things come out to be the same because they'll have the same related acute angle. Once they have a pi involved, they're always going to come back to just x. So cosine of x. Now, the only question is, did it switch from positive to negative? Now I'm going to draw the diagram here to get the rest of the answer. Cosine of pi plus x would be here. I'm going to redraw that diagram from above. There's pi plus x. And it has gone into a tan-only positive quadrant, which means if you want to find the cosine of a pi plus x, you'll get the same answer as what you would get from negative cos x. It has mapped itself into a tan positive quadrant. Another example right from the top. 2 pi minus x, where would that be? It would be all the way around, subtract some x. There's the x in there. What that means is tan of 2 pi minus x would result in a triangle that has its related acute angle x. So tan of 2 pi minus x is the same as just doing tan of x, except it was in a cosine positive quadrant, so it has to change from positive to negative. Now, notice I'm doing some shortcuts now. I'm drawing only a single diagram. That's what I was saying before. A single diagram is enough to think these through. Also, I'm not drawing all the cast rule anymore. I'm only drawing the part of the cast rule that I need. So these are shortcuts that make these questions go a little faster. Okay, the whole explanation again, a third example, doing the same things. Sine of pi minus x. The steps are the same as when we had actual angles. When I was doing 220 and 150, the steps I'm going to do are the same. Draw the angle they're talking about. Pi minus x. So pi minus a little bit of x there. We don't get all the way to pi. There's pi minus x with an x in there in the triangle. That means sine of pi minus x gives a triangle with related acute angle x. So sine of pi minus x will be equal to sine of x. Those two things will give the same answer. The only question is, did I change from positive to negative? No, I didn't. So it doesn't change from positive to negative. They're both positive. These should be memorized. It would be easier if you had these memorized, these three. So some of the other stuff you can produce, you can draw the diagrams for, but these three handy ones, it's just nice to know them. One diagram here for all of these. I'm going to draw the angle negative x. And when I draw the angle negative x, I see that that gives a triangle that has the angle x in it. I know it's negative x, but it's also x in the triangle. So the result of that is that sine of negative x will come out to be sine of x. Cos of negative x will come out to be cos of x. And tan of negative x will come out to be tan of x. Those things, whether you do negative x or positive x, you'll get the same answer. Well, okay, some of them might have changed from positive to negative. See, when we do negative x, only cosine is positive. See, cosine's positive, but these other two are negative. Those are handy little identities to have memorized. When you see sine of negative x, you can immediately write negative sine of x because you'll get the same answer. It's because sine is an odd function. That's why it does that. Cosine of negative x, you'll immediately get positive cos of x. Why does that happen? Cosine is an even function. And tan of negative x, you'll get negative tan of x. Some people just memorize this, that in sine and tan, you can bring that negative out front. It's a lot more complicated than that, but effectively, that's what you do, is you just bring the negative out front, whereas cosine just sort of eliminates that negative. Okay, one more thing, and I referred to this in the opening part of the lesson, is what to do when we're dealing with 90s. Now, I want you to notice something about a right angle triangle. That when we look at the sides of a right angle triangle from x, and when we look at it from 90 minus x, which is the other angle in the triangle up here in the top corner here, the angle C, is that all that's really happened is the opposite and adjacent side have switched roles. And if the opposite and adjacent side have switched roles, then what you get is sine and cosine reversing roles. Okay, what do I mean by that? Let's say I wanted to do sine of angle B. So sine of angle B would be opposite over hypotenuse, would be B over A. Okay? Pretty straightforward so far. Now let's say I want to do cosine of the 90 minus x angle. Well, now the side B is no longer the opposite, it's the adjacent. So from that perspective, cosine of 90 minus x is B over A, adjacent over hypotenuse. Notice what's happened here. Oh, and I wrote that wrong. Sine of... Oh, yeah, no, that's right. So just let me add one more line to be clear. So what I mean is sine of x is B over A, and cosine of 90 minus x is also B over A. Therefore, sine of x equals cosine of 90 minus x. I used this earlier. Earlier in the examples, we did, let me remember what angle I used there. I wrote sine of 40, and I found out the cos of 50 was the same. So let me just write that example down here to bring that back. I wrote sine of 40 will be the same as cosine of 50. So there's three actual relationships here that I'm going to write before I switch over to radians. The one I just found, which is that cosine of 90 minus x is equal to sine of x. But there's two other ones. developed very similarly. Sine of 90 minus x is cos of x, and tan of 90 minus x is cotan of x, actually. The opposite and adjacent switch roles, so you switch from sine to cosine, or from tan to cotan. Okay, those three, you don't need to memorize those, but I would write them on a separate sheet of paper and stick it to the wall of the room that you do your homework in, because it's nice to look up and remind yourself about those. It's convenient to remember those. You can do them in radians as well, so all I'm doing here is changing those exact things to radians. I'm going to add one more, is that tan and cotan sort of go back and forth here. So cotan of pi over 2 minus x is equal to tan of x. You can go back and forth with tan and cotan. That might be clear, but maybe not. The note says that the above should be memorized, and maybe they should be as you move along here. But it's a tough battle with trying to know how much of this should be memorized and how much can I work my way through. What I'll say is, I think it's vitally important you get these ones memorized, the ones with negative x. The ones with 90 minus x, let's just see what happens. After you use them a few times, some people just memorize them automatically after they do a set of homework with them. So, let's just see how that goes. Long term, yes. For speed of getting things done, you want them memorized. How can these be used? 3 tough questions coming here. You need your full attention here. So if you need a break here, go get a snack and then come back. That's a great move, because these examples take all of your brain power. In fact, I'll even say if you get partway through example A and you get confused, I would go and do a bunch of the homework. I would do all of the homework that involves regular angles, like I was doing up here, because those weren't too bad of questions. In radians, I do get all that homework done, and then I do anything that has pi's in it, then go and do that homework, and leave all the stuff that's got pi over 2's, and do all that homework first, and then come back and watch this part of the lesson, because you might be a little bit better prepared for everything I'm about to do in this lesson. I left myself a bunch of space here to draw a bunch of diagrams to be able to handle this situation. Okay, the steps start off the same. Draw the angle pi over 2 plus x, but it is a very strange angle, and I have to make that clear here. When we draw pi over 2 plus x, it's right in here. There's pi over 2 plus a little bit of x. It's a different looking diagram because it's not pi we're dealing with this time, it's pi over 2, and that makes it worse. It means that this angle in here, x, is not the related acute angle. It's not the angle with the x-axis. It's the angle with the y-axis. What a nightmare. How then do I get this angle, which is the one I really want right here, which is the related acute angle, the angle with the x-axis? Well, okay, let me just rewind back to degrees for a minute, because actually the situation here is pretty simple. It's just there's too much going on to see how simple the situation is. Just imagine for a second that x was 10 degrees. And I'll write it in there in another color, because I'm going to erase it in a minute. If x was 10 degrees, what would the related acute angle be? Think about it for a second. If that's 10 up there, this has to be an 80 down here. How do you get that? Well, you take 90 and you subtract the 10 to get the related acute angle. So, if I was going to do this question in degrees, down here I would write just, this is 90 minus x. But this angle isn't in degrees. Or this question isn't in degrees, it's in radians. So after doing that thinking, I go, that means this related acute angle is pi over 2 minus x, which starts sort of a nightmare to go, whoa, that's the craziest related acute angle ever, and your brain starts to explode. Well, don't panic. Let me just say don't panic, because something great's about to happen. But let me first map out what's happened here. Tan of pi over 2 plus x results in a triangle with related acute angle pi over 2 minus x. And your brain's screaming, that didn't help at all. That's just as messy. You've drawn a big diagram to establish something that doesn't help at all. Oh, it helps. Trust me, it helps. Let me just finish the thinking, and then let me show you what I mean. Okay, but we better check to see if this is switched from positive to negative. It's gone to a sign positive quadrant, which means tan will be negative in that quadrant. So the answer of pi over 2 plus x is actually the negative of this answer. Okay, back to the thinking. And I want you to, I'm going to flip the screen back and forth here in a minute to try and help. You go, okay, tan of pi over 2 plus x equals negative tan of pi over 2 minus x. That was really difficult, and it didn't seem to achieve anything because things aren't better. Take a look up here. And this is the argument for memorizing these things. I've got tan of pi over 2 minus x. Look up here. Tan of pi over 2 minus x is cotan of x. So I just straight up replaced tan of pi over 2 minus x with cotan of x. The negative just stayed out front. A wild, wild example. What's the motivation of this? We've got it down to just acute angle x. All that's there is an x now, not a pi over 2 plus x. Why is that such an advantage? Oh, it's going to take a while to make it clear why getting it down to x is an advantage. Within this chapter, we'll start to see why getting down to x is such an advantage. You're just going to have to trust that getting down to just the angle x makes things a lot simpler and a lot more manageable. It's a bit of work to do it. And if you're getting freaked out, I need to tell you, the work's very repetitive. It's very repetitive. Reminds me of teaching quadratic formula in grade 10. When people first see it, they think it's the craziest thing ever. But it's so repetitive. The questions get so repetitive that people eventually go, oh, quadratic formula. I've done it a million times. And that's what these questions are like. We have to practice them and I have to go through them a few times. So with that in mind, I'm going to do 2 more examples that aren't really any different than that example, that just go through all the thinking one more time, or 2 more times. Okay, here's the steps in these. First, draw the angle they're talking about. 3 pi over 2 minus x. This is pi over 2. This is pi. And this is 3 pi over 2. If you're having trouble with radians, draw that diagram on a page and leave it against taped to your wall and look at it every once in a while to remind yourself the big checkpoints here for radians. Pi over 2, pi, and 3 pi over 2. So when you want to draw 3 pi over 2 minus x, it's going to be in here somewhere. There's 3 pi over 2 minus x, resulting in this angle x right in there. Unfortunately, not with the x-axis. It's not the related acute angle. But if the x is with the y-axis, then the related acute angle will be 90 minus that angle, or in this case, pi over 2 minus that angle, and so then I can nicely convert. Sine of 3 pi over 2 minus x results in a triangle that has the angle pi over 2 minus x, so those two things will give the same answer. Sine of 3 pi over 2 minus x results in a triangle with pi over 2 minus x as its related acute angle. Well, okay, just check. Did it change from positive or negative? Yes, it did. It went to a tan positive quadrant, so that's a negative there. Okay, seemingly unhelpful. That doesn't look a whole lot better, but anything with pi over 2's in it, anything with pi over 2's in it can be reduced to things with pi over 2 minus x's in it, which when you first learn them might not seem like a big deal, but it's a huge deal. Pi over 2 minus x can be managed nicely. Look right here. Sine of pi over 2 minus x is equal to cos of x. I can replace that directly. Go back to my pen here. That part there gets replaced with cos of x. Now, I had to scroll the screen up. I had to think it through. I had to worry because I didn't have sine pi over 2 minus x memorized. If I did have that memorized, you would just jump from this line to this line very quickly. So that's the reason why we memorize these things, not to torture you, to make it so that questions like this don't get so scary, because as soon as you see the pi over 2 minus x pop up right here, you go, oh, things are going to be good. Pi over 2 minus x, I know how to deal with pi over 2 minus x. As soon as I see pi over 2 minus x, I'm happy. Okay, I'm hoping that got a little better that time. It's like the second time through the quadratic formula. You go, okay, I'm starting to see it a little bit. One more time, right through it, with just some extra explanations that came from that last example. Cosine of 3 pi over 2 plus x. First step, draw the angle where it goes. And if you're having trouble with radians, knock on these checkpoints whenever you draw the axis. There's pi over 2, pi, and 3 pi over 2. We want 3 pi over 2 plus x this time, so it's in this quadrant here. There's 3 pi over 2 plus another x. And look what's happened to the x. The x is not where we usually want it. It's with the y-axis, which is not the related acute angle. We want the related acute angle. And so that related acute angle is the 90. Subtract that x. Yeah, there's the whole 90 right there. And we got to go 90 minus that x to get our related acute angle. But in this case, I'm doing radians, so it's not 90. It's pi over 2 minus x. And I'm happy to see that pi over 2 minus x. Because I've memorized those, There's me laying the hint again to get those memorized. Once I see the pi over 2 minus x go, I'm home free now. Cosine of 3 pi over 2 plus x is the same as cosine of pi over 2 minus x. That's the related acute angle. And it's in the cosine quadrant, so it stays positive. Look back at my chart. Cos pi over 2 minus x is equal to sine of x, and I've simplified that thing dramatically. Folks, I don't want to claim any of that stuff's easy. That is not easy stuff. It takes practice. The good news is they can be very repetitive. There is a number of questions you can do where you start to go, oh, I can do anything now. You give me anything and I'll be home free. Remember the quadratic formula. There is a point in there when you do enough quadratic formula practice where you go, oh, any numbers. I don't care what numbers you put in the quadratic. I'll be able to use the quadratic formula. And it's the same with these type of examples. Once you get used to all the different angles, and there's basically 3 types of questions here. Ones where they give you the angle. Just say, hey, use this angle here, 220, 150, 200. Then there's questions where they go, okay, we're going to give you an unknown angle x, but it's going to be with pi's. And with pi's, the diagrams aren't too bad. And as soon as there's pi over 2's, it's a different kind of diagram again, and you got to do a different kind of thinking. So 3 different types of questions that you'll basically see there. Just to wrap this up, note throughout this lesson, we've been assuming the angle x is acute. And what if x is not acute? Well, if x is not acute, the diagrams become incredibly hard. Too hard for what we've been doing here today. It got hard enough as it was. But the diagrams become really difficult. But the only good news is they will become really difficult and give the same answers we've seen here. I know that sounds crazy, that you would get the same answer with the angles that aren't acute, but you do. They're crazy diagrams to draw. They're very, very difficult, and it always works. And it has to do with the repetitiveness of sine, cos, and tan, that these things just repeat themselves. And so when angles aren't acute, they jump to other quadrants, and they go back to the positive and negative parts we want. They give the same angles we want, and it really does work out because of the repetitiveness. This says check it out, and I suggest, no, don't check it out right now. Now's not the time to check that out. Just believe that just because we restricted that to acute at the start, we don't have to. That just makes the diagrams easy to draw. Okay, folks, this chapter will bite you, and I mean bad. It will bite you bad if you don't take it seriously. Now's the time to upgrade your study habits. Make study pages of the stuff I've just put up there. Hang them on your walls nearby. Hammer your way through this homework. Do not get down. Do not get upset. Just call out for help as soon as you have trouble with questions. Whatever that means to you, whether you look at solutions, you talk to friends, you email me, whatever it takes, you have to get to the bottom of this homework, or this chapter will build up on you, and things will get completely out of hand, and I mean bad. Okay? It can be done. It's very repetitive stuff. Just do that practice, please. Have a great day.